Alright, well gang, here we go. Final unit. Unit 5. Parametric vector and polar functions. Let's get into it. So yeah, there's going to be 3 sections here. There's going to be, a section for every single one of these items right here. And so 5.1 is going to be about parametric functions. You may have never heard of a parametric function before. A little sort of perspective. It's possible you have, because something like this could be included. It could totally be included, time permitting, into, say, a pre-calculus class. So it's just kind of like another sort of kind of function, and I'm going to tell you about it, and then ultimately we're going to be doing calculus with parametric functions. It's kind of like in pre-calculus how you learned about trig functions. It's y equals the sine of x, y equals the cosine of x. You learned about the exponential functions. You learned about like e to the x and natural logs and stuff. And then in calculus you learned how to do like derivatives and stuff with them. So the first little part of this section is going to be just the background, and eventually we're going to get into the calculus. There's going to be a stopping point. I'm probably going to power right through, but if you want to do this video and this bunch of notes in like a couple of sittings, then go for it. So here we go. Parametric functions. Here's what it is. So the definition of a parametric curve or parametric equations given by parametric equations is like this. If x and y are given as like separate functions, x equals some function of t and y equals some other function of t. So it's like you're defining x and y separately using a third variable, which is going to be t, basically, over an interval of t values. Then the set of points defined by this equation is a parametric curve, and these two separate x and y equations are parametric equations. So it's like we're using this other variable t as like a parameter, and these are all like vocabulary that's not that important. I guess the most important thing is just understand that we're defining both x and y in terms of like another variable t. So here we go. Example problem already. Describe the graph of the relation determined by these parametric equations. And this is like the interval or the t values that we're working with, okay? So over here on this side, it's kind of like a I don't want to say, like, it's a little, I don't know, it's kind of like a little primitive analysis for, that's not a very good way to describe it. But over here, we could generate a bunch of points. Again, we have to like describe the graph. Even if we were going to do it like kind of a cheap way. And then we have to find like a Cartesian equation, which means like a normal, like non-parametric equation. Like almost like a Cartesian means x and y, So over here we're going to take a look at like what the regular equation might be, and it's not going to be so bad, you'll find. So over here, kind of a little basic little analysis, we could say, well, remember our t values are going to be greater than or equal to 0, like literally every value greater than or equal to 0. And so let's say we plugged in 0. If t was 0, we could get x and the x value and the y value. Oh my god. So if t is 0, then x is going to be the square root of 0. And y is literally equal to t, so y is 0. So ultimately, a point on this graph, this parametric curve, is going to be 0, 0. And let's say we let t equal 1, right? Plugging in 1 for t, you would get like these separate x and y values of 1, 1. I think you're catching on. T equals 2, t equals 3, t equals 4. You don't have to, there's no like set rule about like which t values you have to find and how many you have to find. We're just basically ultimately trying to like describe this graph. And like I said, this is kind of like a worst case scenario. We can at least put together a number of points based on like a few different t values. The more t values, the better, right? But if we plug in 2 for t, we're going to get the square root of 2, 2, and then the square root of 3, 3, and then the square root of 4, which is 2, 4. All right. So, but it's probably a bigger piece of the puzzle, or the more important business is probably over here. So we're going to find, because here's the thing, spoiler alert, okay? We're going to algebraically figure out what the regular equation would be, and that is probably going to lead to us realizing what the graph would look like anyway. Like once we're able to actually convert this into like a regular equation, we're going to know what the graph was going to look like. So here's what we do. So think about it, people. We have 2 equations. Right? Wouldn't you think like we can do what you've probably done for years now and kind of like combine them together, or like substitute one into the other? And that's exactly what we're going to do, right? So if x equals the square root of t, then t is going to be equal to x squared. And then we can kind of plug it into that, right? And hey, so we have this, y equals x squared, which is a parabola, okay? But, there's only certain t values. Like over here in purple, this was definitely at least good for something. Even once we know that we're talking about this parabola, but, look at these points, 0, 0, 1, 1, or 2. It's not the entire parabola. Like when we started off with our t values, so we start off with 0, 0, and then we're here, and then we're here, and then we're here. This is only describing, and we could keep going forever. Like we could plug in 1.5, we could plug in 6, we could plug in 10, we could plug in 1,000,000, But we're only going to be like talking about 1/2 of the parabola. In other words, both x and y will be positive, okay? And so that way it's going to be like half the parabola, half a parabola. So this curve is going to be half a parabola, basically, you know what I mean? So, yeah. That's the first example. Again, we're going to be doing all these examples, and hopefully you're going to catch on and stuff. So here's another example. What if we have these parametric equations? So that means if we do, so here's our interval between 0 and 2 pi. Between 0 and 2 pi, we have to, like we're restricting our t values to just this interval. So I think what I'm going to do, just as a little basic, again, you could plug in as many t values as you want, but I think that's a pretty good list in my opinion. And again, you're literally plugging in 0 into both parametric equations to get just a point. So it looks like x is going to equal 2 and y is going to equal 0. And I'm not going to waste precious time right now walking you through every single calculation. I'm going to assume at this point you understand what's going on, just plugging in the t values and getting the separate x and y's, xy, 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 xy. So this starts to tell some sort of tale, I guess. But let's actually find the Cartesian equation. So what are we going to do with these two parametric equations to kind of come up with the Cartesian or like regular equation that we would be way more, familiar with? Well, what do you think? I don't want to just say it so quickly. I mean, I don't know if we're going to be able to do like substitution. Can we like substitute? Maybe we can use a little trigonometry to our advantage. And we could do x squared plus y squared. Okay? So here, x squared plus y squared, let's, you kind of remember how like sine squared plus cosine squared equals 1. We're basically using like the Pythagorean identity, Pythagorean, I mean, you'll see. But we're going to be using some Pythagorean like patterns or strategy kind of thing to do this. So x squared, we're going to square that, and we're going to square that, and see where this takes us. Because again, you kind of remember how sine squared plus cosine squared equals 1. So let's see where this takes us. So 4, and then we can factor out a 4. And like I've been saying, sine squared plus cosine squared is just 1. So we get this equation, which, now here is where we reach kind of an impasse. So here's where I got to call kind of like a timeout. You have the background to look at something like this and recognize it as a parabola. Or if you, for some reason, get like y equals negative x plus 5, I mean, you would recognize that as a line. But there is like a whole other like little handful of different types of equations and their graphs that you've probably never seen, or you maybe, if you have, you've only seen it like a little bit. So there's this kind of category of graphs. I don't even know where I can kind of fit this. There's this category of graphs, okay, that are called conic sections. And it's kind of a shame we don't have time, like let's say in a pre-calculus class or an algebra 2 class, to talk about not just parabolas, but circles. And literally, look at this, conic, as in literally cone, like cross sections of a cone, literally. So they're called conic sections. And parabolas are actually in that category, to be honest. But so are circles, and so are things called ellipses, which are basically ovals, and these things called hyperbolas. Okay? And each one of these has its own like equation form that you've maybe never seen, or like maybe you've seen the standard equation of like a circle, or I don't even know this. I can't remember if this is called like standard form or like the center form or something of a circle. But there's all these different forms, okay? And long story short, too late to kind of, or to get us back on track here. This is a circle because it fits this standard form of a circle, okay? And is it the entire circle? Well, you can kind of go to the t-values and all this kind of like little investigation. And yes, it looks like it's going to be the entire circle. But again, like, I hate to throw, I mean, talk about a can of worms out of left field. But there's these, again, I'm hoping you've at least kind of heard maybe someone like me in the past talk about like the equation of a circle or the equation of an ellipse, which is like an oval. But well, here we go. We're on a steep learning curve here now, people. So the next one, more trigonometry. But first, all of this business. So are we doing 0 to 2 pi again? Yes, we are. And so it looks like we get 3, 0, boom, 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 boom. And here's what we're going to do here. All right. You can't do this like exact setup because here the 2 and the... I'm just going to... I don't want to like have this take forever because these are all like little details, I guess, but I don't know if they're not... Maybe they're not that little details. But we have like the 2 and the 2 match, so that had some sort of impact here. But here we had like a 3 and a 4, and they don't match. And so there's going to be like a slightly different approach, but it's still just using the Pythagorean like theorem or Pythagorean identity kind of thing. So what we're going to do here is we're going to solve for the cosine. And I imagine, look, you know what? I imagine we could do this particular approach. We could have done that on this example. You know, I mean, it's basically the same thing. It's Pythagorean theorem and stuff, or identity. And so we're going to solve for cosine, and the other one we're going to solve for sine. And what do you think we're going to do next? We're going to do that. And we're going to square x over 3, and we're going to square y over 4 to plug into this. And it's going to all be able to be equal to 1. And then, you know, it can be simplified a little bit. And now, again, guess what? Now you have to, like, just sink or swim with this a little bit. I mean, you can, like, you know, maybe I'll also throw this at you right now, which is, I know I keep throwing things at you, but this is a good thing. You can actually take these equations, okay? Look, this is gold, okay? Here, I mean, I can't believe I haven't even said this yet, to be honest. But and you might even know this, okay? Like, you guys know your stuff sometimes more than I do, but with technology and stuff. But you can take these parametric equations and throw them into your graphing calculator. There is a parametric mode. If you hit the mode key, I'm doing it right now on my calculator. If you hit mode, like, you know how you would hit mode to go from radians to degrees or degrees to radians? You see like one option, like one menu below that. You got the function, you got parametric, and then there's a polar, you know. So you would just change into parametric mode. And by the way, you got to make sure you're in radian mode as well. And you would type in these two equations and you would graph it, and you would see that it's an ellipse, you know. So I know on one hand you all of a sudden you got to be aware of these other kinds of conic sections with their crazy looking equations, you know. But you can always graph it on your calculator and sort of just look at it and go, hey, that looks like an oval. And it's an ellipse. Now, is it the entire ellipse? Is it the entire oval? Well, you know, you could kind of investigate that with the t-values and all this stuff. You know, and yeah, like it's the entire ellipse, okay? Moving on. Look at that. One more little example before you might want to take a little rest. But here we go. Same type of example. Describe the graph of the relation determined by this. Only from 0 to 1. Only from 0 to 1. It's not that many. So I'm going to do t equals 0, t equals 1/2, and t equals 1. Again, you can do as many. You could do t equals like 0.25 and t equals 0.75. You could do 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. I mean, whatever. You could do as many t values as you want. But Looks like plugging in only these three, I get the following 3 points: 0, 2, 1.5, 1, and 3, 0, plugging in these t values and getting your x and y's together. Now on this one, I think we're going to be able to do a little substitution trickery. So here's how this is going to lay out. I'm going to have x equals 3t. Turns out that I can say that that means t literally equals x over 3, and then I can plug this into that t in the other equation, like you've been doing for years in algebra, and I get this, right? Wait a minute. This is a line. This is just a linear y equals mx plus b equation. But is it like the entire line? I mean, we're only going from 0 to 1 with our t values. So we started at 0 with this point, and then somewhere in between, like you could sort of say the middle, but I don't know if I want to say that word here. But like, you know, and then you get that point, and then t equals 1, the other like end point, you know. And then look, again, if you were to throw this into your grapher on your calculator, you would realize that it's really just like a segment of the line. It's not this entire line. It's only from 0, 2 to 3, 0. Okay, because we're only doing like these certain t values. Okay, so you can stop now if you want to. I'm gonna power through. I don't know what minute marker we're at right now, but you know, if you're gonna pick this up later, you might want to make note of whatever the time right now is, but I'm powering through to calculus. Okay, here we go. So we're going to talk about, it looks like, slope and concavity, which is derivatives. Okay, cool. So here's how we end up taking the derivative of parametric equations. You definitely want to like bookmark this per se on your notes. You're going to want to keep coming back here to reference this, because if you got to do dy dx, you know, like the first derivative, and you have like the parametric, you know, x equals this, y equals that, parametric equations in terms of t, this is what you got to do to figure out dy dx. And I think this is not a big leap at all. I mean, come on, like this, I mean, you think of it as a fraction. This fraction divided by this fraction, I mean, you get that. I mean, okay, come on, just think about it for a couple seconds. So this is not that big of a leap to wrap your brain around, that dy dx is dy dt literally divided by dx dt. So you're just going to be doing like the derivative of the y equation with respect to t. That doesn't sound so bad. And then on the bottom, you're going to be doing the derivative of the x equation with respect to t. And then just put it together like this. Now the second derivative, that's a little bit tougher to wrap your brain around. But look, the good news is you don't have to understand it. And if you want to understand it, it's right here, man. It's right there. This is a pretty good, I mean, I literally Googled it, you know, and this was like pretty much the first thing that popped up. But if you want to look at this later on and try to understand what the heck is going on with that, I mean, be my guest, but you don't have to understand, you know, how this is true or why it's true. You know, just it's true. And just use this as basically a formula. So the second derivative, okay, of like y with respect to x is going to be the derivative of y, okay, with respect to t, like the derivative of y prime. I mean, I don't want to misspeak, okay? This says the derivative of the derivative, okay? The derivative of y prime with respect to t, right? The derivative of y prime with respect to t, okay? So like this, all over dx dt. But let's see this in action. I mean, I know your head might be spinning a little bit with that, but let's see this in action. I mean, at some point here, concavity, well, whatever. So first, this example. Consider the curve defined parametrically. Okay, graph the curve using technology, and I think I've already mentioned this, didn't I? Your calculator can be put in this par mode. It's from the mode button. But again, not only, you got to remember this, not only does your calculator got to be in that parametric mode, but it's also got to be in radian mode. So try that on your calculator. Pause the video if you need to, and make sure you're able to see this, right? And I believe you can even throw these values in somewhere into your calculator, or you can just kind of like investigate that on paper. If t equals 0, you know, like basically your starting point, okay? Your starting point, your ending point, and okay? You can think of it that way, starting point, ending point, or maybe it's called like initial and terminal. I guess we'll see in a second. Again, this is literally the second time in my life I've taught this, and the first time I ever taught this was like literally 12 months ago. Well, about 12 months ago. So I think it's called the initial or terminal or starting. I don't know. It's something. Who cares? But you could literally find it. You know, t equals 0, so -5, 0. So bam, right there. And then when t equals pi, we end up with, you know, approximately that, which is right there. You know what I mean? So we're only doing like this piece of the entire I mean, this is only a piece of the entire parameter. Anyway, so that was just a graphing example. I don't think that's going to cause you too many headaches. So let's do an example like this. Find the highest point on the curve. How are we going to do that? How are we going to find the highest or maximum point, extreme value maybe? Well, we're going to use the derivative, of course. We're going to use the derivative and then set the derivative equal to 0, right? Yeah, you know. So remember, use this, basically can amount to being a formula for dy dx, right? And the derivative of y with respect to, remember, this is this one. So what's the derivative of 2 sine of t? Well, 2 cosine of t. And then what's the derivative of x with respect to t? Wouldn't that just be 2t? Yep. And so we're going to set that equal to 0. And how are we going to solve this? Like, how do we solve this for 0? Wouldn't it be just when the numerator equals 0? So all I'm going to really need to focus on is when this numerator would equal 0, right? And again, I'm not going to spend minutes and minutes doing these little pieces of the puzzle. I mean, like, I think you won't have too much trouble understanding that, you know, t is going to equal pi over 2 in order for this to equal 0, okay? And again, like, you're literally looking for like I get it. I'm sure there's an infinite number of t values that would make this equal 0, but look, we only care about this particular one that's in between 0 and pi. So yeah, we're only going to go with pi over 2, okay? Come on. And what are we going to do with that? I mean, is that the answer? Is that the highest point? No, we're going to have to, like, why am I doing this? Just to confirm that it goes from increasing, okay. I mean, all right. I don't know how necessary this was, because all this is saying is that, yes, it is confirmation that the derivative is increasing. It's going uphill, and then, yeah, so it is a max here, okay? But, I mean, this is what I really care about. This is the final answer, because we're going to plug in pi over 2 to these parametric equations to get this as our point, okay? So that was using the first derivative, people. Now we're going to find all the points of inflection, which you've known for months to be, you're going to be using the second derivative to do that. So we're going to have to use the second derivative, what's basically a formula. All right. So we're going to be doing the derivative of y prime with respect to t. So dy dt, okay, y dt, well, I've probably been misleading you a little bit. Y prime, okay, was this. You know what I mean? It's not like I think you understand. I mean, I don't want to over-explain this and then confuse you. I mean, this was y prime. Okay, y prime was 2 cosine t over 2t. All right, this. All right, this was y prime, this whole fraction. So, and by the way, could have simplified a long time ago, but whatever. That didn't really matter back then. But so this is y prime, right? So just make sure you understand that, because I think this is definitely like a mental hurdle we got to get over. So this is y prime with respect to t, right? And so we're going to have to take the derivative. Well, we're going to take the derivative of this, okay? And that's going to involve the quotient rule. So you got to do to do dy prime over dt, we have to do this whole quotient rule. And then dx dt was just, where was it? It was just the 2t part. Okay? Whoa, don't want to get ahead of myself. So, whoa, baby. So once again, it's a nasty formula, I guess. But so y prime was this, and so the derivative of that, well, is this because of all the quotient rule. So this is going to clean up, pretty simply, I guess. Instead of dividing by 2t, you can multiply by 1 over 2t. And that's why we end up with 2t cubed down here. And so, remember, to find points of inflection, we're going to set this bad boy equal to 0, right? And there might be a way to solve this. I mean, but you know what? I'm going to show you a pretty easy way to cheat. Throw it onto your grapher, Graph this on your graphing calculator or on Desmos, and whatever the x-intercept is, that's the answer. So when it's ugly and nasty looking, or you just get a little frustrated or something, don't forget, you can always solve an equation by looking at the graph. You know, y equals all of this, and the answer is going to be the x-intercept. So the overall point of inflection, I mean, I guess, see, I don't teach Calc 1 enough to the overall point of inflection. I mean, this would be the entire point, right? But this would just be the x coordinate. Like if you plugged that in to both, to both x and y, you get this entire point of inflection. But I mean, like, you might only need, the x value, right? Or inflection point. What am I pointing at? Why did I point the wrong thing? Point of inflection. I mean, anyway, whatever. But there you go. Then you would take your t value and you would plug it into at least the x equation, maybe both. Whew, that was not the smoothest ride there, but this is the formula. Study the steps of this, especially tracing it back to the beginning, and this part B, which built into part C. You might want to study these notes a couple times here, okay, to kind of get the hang of this. And as well as remembering how I kind of cheated just to solve this equation. You can always do that, though. But we got one more, I think, major topic here, okay? Arc length. Arc length of a parametric curve, okay? And remember, that involves the integral. Well, let me just give you, right out of the bat, the formula that we're going to use to find, the length, the arc length of a parametric curve. So write this down. It should kind of look familiar. I mean, it's basically just like, you probably notice a little Pythagorean flavor in here, but this is going to be how, if you are given two parametric equations, this is how you're going to find, from T1 to T2, what the length of the curve is. So here we go. Let's see this in action. Now, before we get rocking here, I don't know how much space you have on your notes, but I mean, my goodness, this gets continued on this page and even gets continued again. Trust me, it's not it's not that crazy. You might be like, when you see all these steps, I don't know if your heart sinks a little bit. Your heart shouldn't be sinking right now, I mean, because you'll see. So here we go. Find the length of the asteroid. Ooh, fancy math term. Below. So we have, here's our parametric equations. Here's our, T1 and T2 values, basically our interval, okay, to find our arc length. Here's our formula. Okay, so here we're going to be doing dx dt. What's dx dt, people? The derivative of x with respect to t. Well, that's going to be 3 times the cosine of t all squared. But then we got to tack on chain rule. Same with dy dt. Going purple. Yeah. So there we have it. There's dx dt. We're going to have to cram that into this spot. And there's our dy dt. We're going to have to cram all that into that bubble. But cram we shall. Squared. So I've already squared it. So when you square all of this, and when you square all of that, you get this, and then the plus sign, and then all of that. All right. Now look, not so bad so far, right? I mean, seriously, not so bad, right? I honestly at this point I probably shouldn't be jumping back when we're on a roll, but I think this was like the trixiest thing to wrap your head around. Just the whole and but maybe not for you. I don't know. For me, it kind of is, to be honest. The whole like dy prime over dt, and what you had to do. So honestly, look, not so bad. I mean, it's literally a formula. Okay, you'll be fine. And I know there's all, but check this out. The rest of this, people, the rest of all these boxes is just me doing all the integration by hand. You could probably grab your calculator right now and throw this whole thing into your calculator. Where'd this 4 come from, by the way? Squared 9. Well, I'll figure this out in a second. I don't know why this is vexing me right now, but you could throw all this into your calculator right now, okay? Because the rest of this, okay, the rest of all of this, and you can pause and whatever at your leisure and write this all down. But like I've said already a couple times, the rest of this is just integrating it by hand. And the final answer is just going to end up being 6. Whether you do all this by hand or just throw it into your calculator. All right? Now, why was this 4 out here? From 0 to 2 pi. Oh, I think I know. What? What the? Why did I do that? Oh my god. So 0 to 2 pi. Our integral is 0 all the way to 2 pi. Maybe there is a good reason. Huh. Well, just in case there's actually a good reason, maybe you want to try to adapt this little method of kind of breaking this up and not going all the way from 0 to 2 pi on our integral, instead going from 0 to pi over 2 and then just multiplying it by 4, and that would be the same as going from 0 to 2 pi. I don't know, but whatever. So, section 5.1, not so bad. Not so bad. Let me know if you have any questions as you do your homework.